Thank you for watching our presentation on a fast geometric multigrid method for curved surfaces. Linear systems on curved surfaces show up in many places in geometry processing: smoothing data, simulation and animation, and shape analysis and machine learning. One way to solve these systems efficiently is to use a multigrid method. The idea is to solve the system not only on one grid, but on several grids of varying size. Because iterative solvers converge very quickly depending on the grid size, the use of multiple grids improves the convergence of the solver. The basis of a multigrid solver is the grid hierarchy and the associated prolongation and restriction operators that map between the grids of the hierarchy. While hierarchies for regular grids in Euclidean domains are well studied, the construction of efficient multigrid hierarchies for irregular meshes or point clouds is an active research question. In our analysis of related work, we identified two approaches to designing geometric multigrid methods on curved surfaces. The first is to construct a hierarchy of meshes by mesh coarsening and then mapping between these meshes. A recent example is the intrinsic multigrid scheme by Leo and colleagues. This approach obtains efficient prolongation operators that lead to fast convergence. The downside of this approach is a costly hierarchy construction that does not generalize easily to other representations, such as non-manifold meshes or point clouds. The second approach is to represent levels by graphs. The input could be a point cloud, where the edges might be nearest neighbors. Or it could be a mesh, where the nodes are the vertices and the edges are taken from the mesh edges. The hierarchy is then created by coarsening this edge graph of the input mesh, and an example is the work by Shi and colleagues from 2006. This approach results in fast construction and works on any graph, but it has slower convergence. With our approach, called Gravo Multigrid, we seek to combine the strength of both approaches, yielding both fast construction times and fast convergence and working on many different inputs, such as non-manifold meshes and point clouds. We start with a simple idea. What if we could compute downlinear triangulations on the points sampled from the surface, the same way you would do when you're interpolating 2D data on an image grid? Then we could compute prolongation weights using barycentric coordinates. This gives us a couple of nice properties. We could just sample points on the surface and then compute a triangulation. That means we don't need edge contractions. Second, during prolongation, a fine point always receives information from multiple directions from the coarse points, because they form a containing triangle. This is not guaranteed to happen, for example, with just selecting the 3 nearest neighbors. Vice versa, during restriction, each coarse point always receives information from multiple directions around the points. Finally, we keep the number of points in each row of the prolongation matrix to a minimum, only 3. This results in fast operations, like sparse matrix multiplication, during solving. However, computing intrinsic downlinear triangulations is complicated to transfer to different representations and might be expensive. While we do think there's value in trying this, our main goal for this work was to push the efficiency of the hierarchy construction while maintaining solving times and working on different types of representations. The result is Gravo Multigrid, which gets its name from the use of graph Voronoi cells during construction. Gravo Multigrid consists of the following steps. First, we sample points from the surface using a fast sampling strategy. Next, we compute a graph Voronoi diagram, followed by the construction of triangles based on this diagram. Finally, we compute prolongation weights using barycentric coordinates. Let's look at these steps in more detail. In the sampling step, we look for a spatially uniform set of points on the surface. We use an algorithm based on the maximum independent set. We sweep once over the set of points, picking one point at a time if it is eligible. At the start, all points are eligible. When we add a point to the sample set, we mark the points within a geodesic ball of radius r as ineligible. This radius r is based on the fraction of points we wish to keep and the average edge length. We repeat this until we've passed along all points. On curved surfaces, we use a geodesic ball and only search the 2 ring for marking points as ineligible. This is a trade-off between efficiency and achieving the desired sampling ratio. Next, we construct a graph Voronoi diagram around each point. This is done with a fast multi-source Dijkstra algorithm. Each sampled point now has a graph Voronoi cell around it, defined on the points in the finer level. This is where our guiding idea of using Delaunay triangles shows up again. For a continuous Voronoi diagram, the Delaunay triangulation is a dual of the Voronoi diagram. We mimic this idea by creating triangles from the edges connecting neighboring Voronoi cells. On a curved surface, that looks like this. The red points are the non-sampled points, and the triangles are the ones we want to find with our algorithm. The result is a highly uniform triangulation because of the uniform sampling, and we get nice, regular triangles. On the left, you see our result, and on the right is what would happen if you consider any triangle in the one ring. These bad triangles result in worse convergence and use more time in later stages because we have to consider more triangles in subsequent steps. We repeat this process for each level and find for many types of shapes that we get remarkably nice triangulations. Given these triangles, we compute prolongation weights by performing a closest point projection to this triangulation and then computing barycentric coordinates. These are then stored in a highly sparse rectangular prolongation matrix, which is used in the multigrid solver. Let's recap. We now have a way to 1. Take in any mesh or point cloud, downsample our input quickly to get a hierarchy of points, and then compute a fast triangulation for each level that can be used to get prolongation weights. Let's take a look if we can also solve much faster. In this talk, I will focus on the comparisons that we did. We have a set of ablation studies in the paper that pick apart each choice in the algorithm. In our comparisons, we compare against the methods by Shi and colleagues from 2006 and Liu and colleagues from 2021, and look at two things. How fast can we construct the hierarchy, and how fast can we solve or converge to a solution? We also compare to other algebraic multigrid approaches, and for reference, compare to direct solvers. We tested on over 50 input shapes, including non-manifold meshes and point clouds. Now, for some of our main findings. During construction, we're only 1.8 times slower than the graph-based approach by Shi and colleagues. But we're 36 times faster in construction than the intrinsic multigrid method by Liu and colleagues. With regards to convergence, we see similar behavior to Liu and colleagues. In our paper, we show convergence plots for a number of shapes. In many cases, the results look like this. Liu and Gravo multigrid converge very quickly, while the graph-based approach struggles. If we now include the hierarchy construction time, we see a clear benefit of using Gravo multigrid over previous approaches. When comparing timings for a fixed target tolerance on a Poisson problem for over 50 shapes, we find that we are 3% faster than Liu and colleagues, showing that we maintain the fast solving behavior, and we are 274% faster than Shi and colleagues, showing that this geometric approach increases the solving speed. Finally, we show how our approach can be useful in applications, building on previous work. For example, in data smoothing, conformal flow on a non-manifold mesh and polygonal meshes, and in simulation. We hope that you will find Gravo multigrid useful for your problems and are happy to share our code at graphics.tu-delft.nl/gravo_mg. You can also include our solver as a library in C++ or use it directly with Python through pip install Gravo multigrid.